Yeah, welcome everyone. I'm happy to introduce Nick Erickson as our speaker for today. He's going to talk about AutoML in the age of structured foundation models. Nick is a senior applied scientist at Amazon Web Services. He has worked on a lot of stuff related to tabular data, AutoML systems, and specifically structured foundation models now in the recent times. And today we're going to learn a lot more about his recent work, I think. So the floor is yours. Thank you very much for being here.
Yeah, thanks so much, Leonard and Aaron, for inviting me on. Super happy to be back for another talk at the AutoML seminars. Structured foundation models. I feel like a pretty big deal. It's going to become more and more important as more and more people catch on to the fact that, hey, it actually works and it works quite well. So let's just dive into things. Um, so. Before we talk about structured foundation models, I think the first idea that a lot of people had was large language models for solving tabular tasks. You know, what if we could just put ChatGPT or Claude or something like that and throw it at tabular data somehow and have it generate predictions? And that just automates the whole process, right? It's like, you know, you just turn your tables into text, you flow it into some magic thing, the magic thing produces the best result, and that's the system, right? You could throw away XGBoost, you could throw away all of data preprocess or like, you know, pretty much everything, right? If that actually worked. So why am I talking about tabular data specifically? So tabular data is ubiquitous in everyday use cases, shipping cost estimation, product similarity matching, user term prediction, many, many, many more. Basically, the most convenient format to put data that companies have found is a table, generally speaking, and they have many of them, and that those tables have very important information. And so it's ubiquitous everywhere. And so being able to predict with high accuracy given these tables is important. So if we wanted to use an LLM out of the box, right, for tabular data, you'd first need to convert it to natural text because LLMs are pre-trained on basically the text from like the internet, like Wikipedia. And so they don't really know tabular data in the sense that XGBoost, for example, or multi-layer perceptron knows tabular data. It doesn't ingest it in the same way. And so you need to take this table and convert it to raw text. So there's several ways to do this. You can serialize it via a manual template. You take a given row of data and you say for each column, the column one is value one, the column two is value two, as in this manual template. Um, there's other alternatives. You can even use an LLM to try to make it more natural in terms of the wording. And then you can add a task-specific prompt to try to get the LLM to basically answer what the correct income or basically target variable is here. Uh, and note the task-specific prompt is you need to inject um, context about the actual problem itself here if you want to have something task-specific, which is not something that like XGBoost, for example, needs. And so you can also fine tune the LLM using labeled examples, either actually fine tuning it or via in-context learning, which is a bit more frequent. Um, and yeah, you can also then predict on new samples. And so there was a paper, TabLLM, that's one. And another one was very recently, Tabula 8b at NeurIPS 2024. And basically the idea here is basically just a more sophisticated version of TabLLM, I would generally say. And it has a specific um, serialization method. They pre-train the model on a bunch of tabular data, this Tabula model. And then they basically can show better random guess performance even with zero samples of training data, just like zero shot prediction. And it can basically do quite well on few numbers of data, so like few shot learning. And this kind of makes sense because the idea is that this LLM is leveraging information such as the column names and then basically knowing that date generally means something, precipitation, temp max, and weather, right? So it's like rain and sun, it makes sense that if precipitation is high, then the weather is probably less sunny, right? So you could imagine that the LLM could get something out of the fact that it's pre-trained on the internet for this kind of a thing. Um, but note the one weakness here. This is a single row of data. It's an entire big paragraph. And their LLMs have context lengths. They're already pretty slow. So there's a big trade-off going on here. And this is why we're only looking at few shot here, because if you want to fit a lot of examples into the context, you run out of the context window. And even if you could fit it into the context, it starts to become unbearably slow. So what happens is first, other models, traditional tabular methods, improve faster as they gain additional data than the LLM does. So they quickly start to eclipse the LLM, and the LLM eventually can't even get more samples. And so when you have more data, it just gets outperformed by the traditional methods. And then also, the LLM has many, many other restrictions. For example, the more features you have, the harder it is to fit all of it into context for a given sample. It doesn't really understand the numbers probably as well as categorical features. I think categorical features would be its strength. It needs informative column names, right? Otherwise, it's not that good. There are other things. It can be leaking. So it could have just memorized all the data sets that we're talking about right now because it's pre-trained on the internet. And these data sets that people generally benchmark on are data sets that are academic data sets that are available everywhere and constantly cited everywhere and with the raw tables everywhere, and they're generally pretty small, so it's easy for the LLM to ingest it and learn it all. So who knows, really? There are some papers like in the Tabula, they do a ablation study to check basically if there's memorization going on. It seems like there's not a lot, but it's always a worry. Um, okay. So basically, this is very interesting, but I think we aren't quite there yet for LLMs for tabular data, at least in the broad range of cases. And so now I want to go back to kind of the general tools that we have learned to use for tabular data. And this involves data preprocessing, traditional model training, model selection, cross-validation, ensembling, all very strong components to a data science pipeline, and specifically to what we know as AutoML systems. Basically, a bunch of best practices that, when combined together, get you good results on average. So AutoGluon is an AutoML framework that is able to get you fast and accurate ML in just 3 lines of code. It's widely adopted in industry and in general. It's fully open source. Yeah, and so you can just check it out on AutoGluon. You can just Google it. It's on GitHub. So AutoGluon makes machine learning easy without compromise performance. Again, just 3 lines of code. You specify the label column you want to predict. You call fit on your training data. You call predict on your test data with the trained predictor. And AutoGluon is currently the state of the art in ML competitions. So in 2024, AutoGluon became widely adopted on Kaggle. And basically, it was used to finish in the top 3 in 16 out of 20 live Kaggle competitions in 2024 for tabular data, and never was outside of the top 1% of solutions. Basically, in every single competition, someone used AutoGluon as part of a solution that achieved a top 1% on the private leaderboard, with over 1,500 average competitors per competition. So how does AutoGluon achieve good results? So it maximizes diversity by training a wide suite of model families with different hyperparameters. Now, you normally think of like hyperparameter optimization here for most AutoML systems, but AutoGluon doesn't actually do hyperparameter optimization during the user's fit. Rather, we learn an optimal portfolio of models through something called TabRepo, where basically we store many, many results on many, many data sets of many, many configurations. And then we're able to actually learn the optimal ensembles of these methods and build portfolios that work well on average on new tasks. Um, so instead of doing HPO during the user's fit call, we kind of do it beforehand and then take the learned best configuration on average, and that's what the user gets. Um, and then we apply something called multi-layer stack ensembling. Um, I'm not going to go into the nuances of multi-layer stack ensembling here, but the general idea is that you use the predictions of models as features to other models. And this ends up being very powerful and is able to get you a better solution on average than if you weren't doing this. And additionally, we do model bagging, which is a well-known technique to improve performance. And if you're more familiar with like large language models recently, you could think of this somewhat akin to mixture of experts, where basically a lot of the components map to similar things, right? If you have a LLM judge that takes input from expert LLMs, which are kind of given contexts of, hey, I'm a mathematician, hey, I'm a physicist or whatever, right? They'll give you varied outputs, and then that all feeds into the judge LLM, which then kind of combines those outputs into an informed decision when taking in the original input of the problem to give you a better solution on average than any of the individual experts themselves. And that's kind of what multi-layer stack ensembling and a weighted ensemble is doing. It's just with a multi-layer stack, it's like you have multiple layers of judges. Yeah. So going back to LLMs for solving tabular tasks, I would say it's not the best option yet for tabular data, except maybe for few-shot learning. But again, I would say that this is very much a work in progress, heavy research heavy area, and I wouldn't necessarily recommend it for production use cases yet. If you have a very specialized problem and you can verify that you are not encountering memorization issues and you see it's working well, then go for it. But just keep all of those things in mind and also the performance issues in mind. So LLMs might not quite be there yet for tabular data, but what about foundation models for solving tabular tasks, right? What if we don't convert everything into text and feed it into an LLM, but rather we work in the space of where tabular data lives, right? So this leads to tabular foundation models, or not, which are non-LLMs. This is a non-exhaustive list. I probably missed a lot of things. Forgive me in advance. So we have TabPFN from July 2022. It's the first tabular foundation model, I think, and it predicts via in-context learning. It has a transformer architecture. It's pre-trained on purely synthetic data, and it has row-based attention, where the row is the token. And it seems to work pretty decently. In my testing, I think it kind of falters a bit on harder data sets than the ones in the paper, particularly, I think, categorical features and like missing values. I think it struggles a bit. It also only worked on very small data sets, around like the 1,000, 2,000 samples. And then beyond that, I think it didn't work quite as well. But it was promising. It was able to get very strong results on certain data sets. And in particular, being pre-trained on synthetic data fully was very, very interesting. Next up is XTab. I probably missed a couple between these two time ranges. So XTab is a work that I was a co-author on, and it's cross-table pre-trained weights for FT transformer using real data. So basically, you do like a federated learning setup where you're training the model on 100 data sets, and then you're kind of uh, like averaging the weights together and updating the weights as you do your training. And this isn't a tabular foundation model in the same way TabPFN is, whereas TabPFN you can predict by in-context learning. XTab you need to fine-tune the model on every new data set. This is just a better weight initialization. But we were able to show that you can get about like a 65% win rate or so versus the randomly initialized xtab weights if you then fine tune both of them for some amount of epochs. But the benefits of doing this decrease the more epochs you fine tune on a new data set for. So basically, if you only fine tune for one epoch, then doing this is really good. But if you fine tune basically until you stop gaining performance improvement on a validation set, then it becomes fairly minimal, the improvement. But this is another way that you can get improvement basically by pre-training a model. Then MotherNet in December 2023, which is a hypernetwork architecture, is pretty interesting, but I don't think that it ended up performing all that well. Then there was CART, graph-based tabular foundation model, which is a little bit different from the other methods that are on this page, and I haven't dived into it super deeply, but it's definitely very interesting. Then there's TabForest PFN in May 2024, which basically improved TabPFN via pre-training on model predictions fit on random noise, which was very, very interesting. Basically, TabPFN had certain assumptions about what the prior for the pre-training should be. Basically, that it should mimic real data and it should be sampled such that the data sets are realistic. Whereas in the TabForest PFN paper, they first had TabForest, which is something that completely abandoned the prior of TabPFN and only used model predictions fit, or basically, I think it was decision trees or random forests fit on random noise as the pre-training data, and it was able to be better than random on real tasks, basically, which is very interesting. And when you combine that, basically, if you mix the TabForest prior with the TabPFN prior, and then you pre-train that with some weighting of the two, you get TabForest PFN, which significantly improved upon TabPFN, but it's like the same architecture. So that's pretty interesting. Then we had Attic in September 2024 by the same author as TabForest PFN. So it's similar to TabForest PFN, but it also includes a cell-based attention where the entry as a token. And this performed much, much better as well. Then there was TabDPT in October 2024, which was pre-trained on a huge suite of internet-scraped real tabular data. And it seems to perform pretty well. At least in my testing so far, it's not as good as the cell-based attention models, but it seems to be pretty interesting. And it's notable that it was not pre-trained on synthetic data, whereas the others, with the exception of CART and XTab here, were pre-trained on synthetic data. Then there's TabPFN Mix, again by my team in November 2024, which is similar to TabForest PFN with a better prior. Basically, TabForest PFN, the only model it used for augmenting the prior was, I believe, it's either decision tree or like random forest. With TabPFN Mix, there's no paper for this yet, but basically you can think of the natural next step is to incorporate other model families as part of that data generation for the prior. And this leads to better performance than TabForest PFN by a notable amount. Then there was TabFlex in December 2024, which is linear attention, and it claims to support millions of samples. I don't believe there's any code, or I don't know for sure, but I don't think that there's code available for this yet. There might be. So there's that. And then now we're getting into like the very much like the work in progress or very recent stuff. So now the big one, TabPFNv2. This has also cell-based attention like Attic and a strong prior. The prior is not fully explained, but we can assume that it's basically what TabPFN does, but much, much more sophisticated given the basically the 2.5 years of work that was put into it beyond TabPFNv1. And it has what I would call astounding in context learning performance. And what I mean by astounding is that in the domain of dataset scale that it claims to be performant on, it is basically unparalleled. It beats pretty much everything, and that's very impressive, in a word. Then we had TabICL in February 2025, which has better scalability than TabPFNv2 and removes the max class limitation. And in my testing, it's almost as good as TabPFNv2 on small data sets. And for medium to large, it's either equal or better. But this is still very early preliminary stuff. The other thing about TabICL is it's much faster inference time than TabPFNv2, and I believe it also uses less memory, but I would need to double check that. All I know is that it's a bit more stable in my benchmarks. Um, and also, TabICL is also cell-based attention. So I think one big takeaway is cell-based attention seems to be much better than row-based attention, just across the board. I think if you're doing a tabular foundation model and you're doing row-based attention, just switch to cell-based attention right now, I would say. It's very, very, very good. Um, from my experience, so the three that do this, so Attic, TabPFNv2, and TabICL, of the things that I've tested, they are by far the best of all of these in terms of performance. Um, so I'm going to focus in now on TabPFNv2. So basically, this has you basically sample from some prior, which is basically inspired by like Bayesian, where you have correlations between all the features. You generate a graph. That graph does things to sample values, and you generate synthetic data sets through it. Millions and millions and millions of synthetic data sets, and you just pre-train the model for a very long time on these, and you keep tracking if it's getting better, and you decide to stop at some point. Um, and this gets very, very good performance. So if you're less familiar with, the history of tabular data, CatBoost has been the king for probably, I don't know when it came out, but whenever it came out, like 7 years or I don't know, a long, long, long time, 6 years or something. And before that, it was like XGBoost and LightGBM, these tree-based models. And for a very long time, it's always been all these papers that have said like deep learning versus trees, and it's all about trying to get deep learning to finally beat trees. Well, this beats trees on the scale of data sets that it supports, which is basically less than 10,000 samples, less than or equal to 10,000 samples, less than or equal to 500 features, and less than or equal to 10 classes. And I will say on the upper end of that range, it's debatable if it's actually better, but definitely on the lower end of that range, it's very better. And very interestingly, the prior state of the art for single models was CatBoost, but for any method, like anything goes, it was AutoML, right? And so they even showed that they can outperform AutoGluon, which was the top performing AutoML system in the 2024 AutoML benchmark, in this like domain of data sets, this small data set or small size data set domain. Both with just normal TabPFN, but also with basically an AutoML system version of TabPFN called TabPFN post-hoc ensembling. And notably, if you look at the x-axis here, you can see the average fit plus predict time. The claim is that basically that with a GPU, you can get results that are competitive or exceeding a top AutoML system in seconds, which is a huge step change in terms of what is possible. And this was published in Nature in January. So one interesting thing, right, is that tabular foundation models offer the potential of AutoML grade user friendliness with the elegance of a single model implementation, right? The claim to fame kind of AutoGluon and AutoML is just 3 lines of code, right? Well, TabPFN also is just 3 lines of code, right? It handles missing values, it handles categorical features, right? It's basically its own self-contained AutoML system in a sense, right? If we think of AutoML system less from what it is doing internally and more about what the user experience is and the user interaction is, right? You can think of this model very close to what an AutoML system is. And let's think about some of the trade-offs here, right? So what are the strengths? So it has fast training time or no training time if you're just doing in-context learning. It's easy to update. So, if you want to release a new version of your foundation model and you aren't doing some huge architecture shift, you're just updating the weights. And if you do an architecture change, well, it's all just written in Torch anyways. It's not like super hard probably to do. It's also low risk of tricky bugs for the user, whereas AutoGluon at inference time is 100,000 lines of very, very high precision code that if one line of code is wrong, everything might break. For a tabular foundation model, I mean, yes, it depends on Torch, but really it's, just a transformer architecture that's very you know, well understood in terms of how it actually performs inference, right? And so you just download this tabular foundation model weights, you pass the data through, and you get your prediction. And it's like pretty straightforward and simple. And so, yes, you can have bugs and stuff, but I think the amount of possible bugs and the difficulty of which to resolve them is much less than with a full-fledged AutoML system that's doing multi-layer stack ensembling and parallel processing of multiple model families and all these different dependencies and stuff, right? It also has much less overall developer code. As I said, AutoGluon, 100 plus thousand lines of code. I could imagine somebody could, make a tabular foundation model in just a couple thousand lines of code. Um, Potentially less. I don't know exactly how little you could go, but right. It's once you're able to define your prior, you're able to define the pre-training loop, then you get your model and then you just write some code that is able to process new data, and that's your whole thing, right? So pretty lightweight in general. Again, you can always go much more, right? I could also say that you could make an AutoML system in less than 1,000 lines of code. You probably could make a pretty good one in less than 1,000 lines of code, but once you like really want to go up into the upper ranks in terms of like getting as much out of it as possible, the amount of code you need is exponential, kind of. So what about some weaknesses? So it has slow inference time and or reliance on a GPU. It only performs well on tasks with less than or equal to 10,000 samples, less than or equal to 500 features, less than or equal to 10 classes for TabPFNv2. But this is just a current day limitation. Um, I think the more pressing thing is that attention is nonlinear in terms of the memory usage. And so your memory usage is really the big bottleneck in terms of number of samples and like features that you can have. And maybe, linear attention or some tricks like what's being doing in TabICL is the thing that will solve those things, but that's like the current concern. It's monolithic. Basically, it's just one model. You take it or leave it. And this is both a strength and a weakness. The strength is it's simple. The weakness is that if you want to kind of get just a subcomponent of this thing, you can't because that's what it is. It's a model. And it has a large disk artifact relative to optimized alternatives such as trees. So if you care about having a really lightweight thing that's running, it's basically you're going to have your 9 million, 10 million parameter model and that's what you have to have, right? Whereas with a tree, you could have a very shallow tree for a very simple problem that you need to be very fast, things like that. And it's also not yet heavily tested in complex scenarios, such as competitions in industry. Mostly what's been done is like the academic data sets, or basically what is available on stuff like OpenML. But real data sets, real competitions, historically have always shown that trees outperform compared to what they are scored at on like academic or benchmark data sets. So I feel like real data and like real scenarios lend themselves very nicely to basically the prior of a tree. So there's that to also consider. So I want the big takeaway I want is that if a new model beats AutoML, then let's just add it to the AutoML system, right? So the idea being if TabPFNv2 outperforms, say AutoGluon, well then what we as AutoML practitioners should think about is why don't we just add this thing to the system, right? Because AutoML is the what I like to think is like the best combination of available tools and tricks uh, put into one place, right? And so if a trick beats your system, then why not use the trick? So um, to give an idea, right? Let's say that AutoGluon has XGBoost, and then, with AutoGluon 1.2, we released TabPFN mixed, which improved AutoGluon here, right? And then, well, we could just add TabPFNv2 as well, right? And all of this is just parts of this multi-layer stack ensemble architecture, and adding these things consistently improves the performance of the system, right? Again, you have to contend with the trade-offs of the shortcomings of these models, like slow inference time. But if the user doesn't care about those things, or if it still satisfies their constraint, then why not? Just go for it. Um, and this is across 109 datasets on Tab repo. Note here that AutoGluon in my benchmark here, AutoGluon like 1.0, for example, is outperforming TabPFN v2. But with that said, this isn't a very heavy and formal study. And I think it's because the range of scale of size of data sets is bigger on average than in the TabPFNv2 paper. So I think that's probably a part of it. And also, I don't think I did like a full, I didn't do like the post hoc ensembling stuff or like having n estimators 32. I forget what it was. But hopefully I'll have a more formal study later on. But the fact of the matter is it outperforms all of the other traditional models by a lot, right? Um, so what would need to happen for AutoML to become obsolete? So this is one thing. The question is kind of like, should everyone just start working on tabular foundation models and throw AutoML out? And basically, it's just a battle of who can be the best foundation model. So what would need to happen to just abandon AutoML as a field? Uh, it would need to have one model to rule them all, is one component. So basically, where no selection strategy meaningfully outperforms selecting one specific model configuration to fit and predict with on every task. And that the model lacks meaningful customization and is Pareto optimal in basically every dimension. So it's like it would be hard to make an argument that this model is less suitable than anything else on any task. That's a really tall order, right? You need to be very fast inference, very fast training time, low disk usage, top of the line accuracy, right, across the board, and just works on all scales of data sets. And then on top of that, there needs to be no improvement in modeling afterwards. So basically, no new models are released that compete with or outperform the previous state-of-the-art model. And this is because even if an AutoML system doesn't outperform the best model, it can still provide value simply by being an up-to-date pointer to the best model as it changes over time, right? So the idea being that if you think about someone in industry, they are going to solve a problem on day one, right? And then on day two, time moves on, and they might move on to a new project. And then later down the line, that solution they did on day one becomes legacy. And in order to justify updating and improving a legacy solution, it's like in order to do that, you really need to have a very good justification for like what is one, like that it's actually an improvement to what you're doing, but also you don't want to mess with what was what was coded up before. So you want to make as little changes as possible. So the smallest possible amount of change you could make is just a upgrade of the version of the thing you were already using, right? So just pip install upgrade, like, upgrade AutoGluon to the next version or something like that, right? Same API, same everything. You can also do this with like TabPFN, for example, right? If you're using TabPFN, just upgrade to the next version. But what if 2 years down the line, TabPFN isn't actually the best thing that exists anymore? What if there's a new tabular foundation model or TabPFN v3 or something, right? And the person in that industry solution doesn't necessarily know about that, right? They're a domain expert, but they're not a machine learning expert necessarily, right? And so they're going to fall behind. That thing is going to fall behind. But if they were using an AutoML system that basically, when they upgrade it, it actually just points to whatever the best thing is, right? It goes from XGBoost to looking at TabPFNv2 to looking at, an ensemble of TabPFNv2, TabICL, or whatever, right? Then that could provide value, even if it doesn't necessarily outperform whatever happens to be the best thing right now, just by the fact that it's able to consistently represent whatever an approximation of the best solution that you could come up with at any given time. So basically, with this, I'm going to say AutoML is not becoming obsolete whatsoever. It's not even close. And I think having AutoML systems that really heavily interact with these tabular foundation models is a very interesting area that is ripe for a very cool research paper. So how can AutoML leverage tabular foundation models? Let's talk about the synergies between AutoML and tabular foundation models. So in my opinion, in order of increasing complexity, just fit multiple foundation models, use whichever works best. And then you can also start satisfying user constraints like time limit, infra limit, disk usage. You can fit a weighted ensemble of the foundation models. You can do diverse feature preprocessing, kind of like in TabPFN's post hoc ensembling method. You can ensemble them with traditional models and try to increase diversity that way. You can meta-learn a model portfolio like we do in TabRepo. And then you can stack ensemble like we do in AutoGluon. So how about tabular foundation models leveraging AutoML? So this is more preliminary ideas, and I'm just kind of brainstorming here, and feel free, afterwards during the Q&A, chime in on your thoughts as well. So what if we think about pre-training of tabular foundation models from the AutoML perspective with the goal of achieving the best ensemble solution? So ensembles work best when they have strong, diverse models to build off of. So what if we change our pre-training goal from obtaining the best single model to pre-train to obtain the most diverse complementary set of foundation models? So how would we be able to do this? So to give an idea, TabPFN post-hoc ensembling tries to inject diversity at inference time by performing different pre-processing to the data and passing it to a single model checkpoint. But what if we did the same thing, but at pre-training time instead? Basically, we pre-train n tabular foundation models on different distributions of data and ensemble them on new tasks. So we don't need to necessarily even ensemble them. We could have domain expert foundation models that an AutoML system could select via meta-learning, or you could even use a large language model with appropriate business context. If you're able to map these domain experts to specific types of tasks and then detect those tasks via some context about the new task that you're given, such as a business document or the column names. This is wide open research, I think, but I think it would be very interesting. And this leads into where I would like to announce a call for papers for the first ICML workshop on foundation models for structured data. I, along with Leonard, who is in this call, and others within the tabular and time series learning communities, are organizing a workshop for focusing on how to build structured data foundation models. We have speakers, including Frank Hutter, who is here with us, but also Jan, Mihaela, Josh, Andrew, and Hao, who are all authors of these structured foundation models. And we want to really hone in on what is the best way to go about doing these things, building foundation models. How do you construct the prior? Do you use real data sets or synthetic data sets? How do you choose what data sets to use, or how do you generate the synthetic data? How about benchmarks for structured data foundation models? How do they fare compared to traditional models and to each other? What is their limitations? What about LLMs for structured data? Can we get something that competes with traditional methods or foundation models? What about critiques? What are the shortcomings? What are the tabular foundation model papers not telling us? Or the structured foundation model papers not telling you? And also, what about real-world applications? Basically, yes, it works well in academic data sets, but what about on real industry applications? Those are all of interest and more. So please check out the website. And we are looking forward to people submitting, and seeing you at the Vancouver Convention Center in July this year. So coming soon, some things I'm working on or my team is working on. Tab Arena. So Tab Arena is going to be a large-scale evaluation of traditional tabular methods and tabular foundation models. Basically, if you can think of the model, the goal is that it's in Tab Arena. And with the goal becoming the living benchmark for tabular data, somewhat akin to what Chatbot Arena has become for LLMs. Basically, a living leaderboard where if someone says, actually, I think that this model is stronger than what your leaderboard says, then they are open to providing a configuration for that model, running it, and basically posting an updated, better result. And the hope is that we can work with the community to make it so that this is also a very easy thing for people to develop methods on, right? So if you're developing a new foundation model method or any method for tabular data, that you can leverage this Tab Arena for quickly iterating on your model implementation and comparing with the very best. Also, coming soon is Mitra, which is a new tabular foundation model. It's a follow-up on TabPFN mix. It uses cell-based attention. It focuses on fine-tuning performance rather than in-context learning. So that's one big difference between this model and TabPFNv2. And it is currently work in progress, but hopefully I can share more at a later date. And AutoGluon 1.3, where we're going to support real MLP, TabICL, TabPFNv2, Attic, hopefully Mitra, etc. So basically, in AutoGluon 1.2, we brought TabPFN mix as a tabular foundation model into AutoGluon. It is an experimental model, and that seems to work pretty well. And these cell-based attention models are even significantly stronger than TabPFN mix. And I'm seeing really promising results in some early benchmarking. So looking forward to it. And real MLP isn't even a tabular foundation model. It's just a really, really, really good multi-layer perceptron model. And if you happen to have an AutoML system that you are building, include real MLP. Do it. It's very good. Yeah. So with that, I think we can move to Q&A.